Good afternoon, everybody. My name is George, and today I will be presenting a tool called ProFL. So, the motivation behind this tool is that in the field of software testing, there seems to be um, research on fault localization, but only on imperative languages. So, the research ignores declarative languages like Prolog. This is partly because fault localization is already a difficult task, and trying to perform it on a declarative language just makes it more difficult. So what is fault localization? Fault localization is just the automation of the process of locating which line, function, or class is responsible for a bug. So the goal of fault localization is not to fix a bug, but rather to suggest lines of code that might be responsible for that bug. So the difference between an imperative and a declarative language is that an imperative language lists out how to get what you want step by step, whereas a declarative language just kind of tells you what you want, right? So Prolog is not executed procedurally. So Prolog works by the system reading in the program and the statements that you declare and then storing it in what they call a knowledge base. Then the user will type a series of queries, which the system will try to answer based on the knowledge base. Sweet Prolog is the most commonly used environment for building and executing Prolog models, and it has this nice library called PL Unit, which allows you to run unit tests with Prolog, which is what we leverage with our tool. So our tool is divided into 4 components, right? The coverage engine, mutation engine, and 2 fault localization techniques. So I'm going to step through each one of these. So the coverage engine, in Prolog, there's no native way to determine test coverage, which is an integral part in fault localization. So what we did is we based our coverage technique on a recent paper which uses mutations to determine test coverage. So first, we invoke the mutation engine to get all the valid mutants of the program. And then for every mutant, we execute the test suite, and we see if any of the test results change. If a test changes, then we conclude that that statement that was mutated is covered by that test. The mutation engine finds all the valid mutants of the Prolog model. So there are certain mutations that don't change the meaning of a program, and also there are mutations that might cause a program to crash or create an infinite loop, so we watch out for that in the mutation engine. Our first fault localization technique is a combination of spectrum-based fault localization techniques, and these techniques use test cases, pass and fail results, and the coverage information of those tests to calculate a suspiciousness value. So these formulas for each statement weigh the total number of failed tests that cover that statement, and also the ratio of passing and failing tests that cover that statement, and then come up with the suspiciousness value. The higher the suspiciousness value, the more likely the line is to be the source of the bug. Our last fault localization technique is a mutation-based technique, and it's based on 2 assumptions, right? So if you mutate a faulty statement, the probability that the mutation causes a previously failing test to pass is higher than mutating a correct statement. This is because mutating a faulty statement sometimes fixes the program. If you mutate a correct statement, the probability of that mutation to cause a previously passing test to fail is higher than when mutating a faulty statement. This is because mutating correct statements introduces new faults into the program. So if you were to run ProFL, this is the output you would get. You get 4 tables, each one representing the result of one of the techniques. You can set an argument so the ProFL only executes the spectrum-based or the mutation-based techniques, or both. If you choose spectrum-based, you can choose which spectrum-based formula it uses. So these are the results of the experiments we performed on 10 Prolog models, and the table shows the number of lines and tests that each of the model has and the runtime of our tool on these models. And then we see the ranking of the faulty statements. The numbers mean the place in which the faulty statement was ranked in terms of suspiciousness value. So even though we allow the option to use one or both techniques, we recommend using both the spectrum-based and the mutation-based techniques, as one technique might be more accurate than another depending on the test case. So one of the things we want to do for our future work is to improve our coverage engine, because it sometimes gives us false negatives. And also we want to test our tool against larger Prolog models. So I'm having some issues connecting to the Slack and getting the Zoom link to present and answer questions. So what I'm going to do is take some of the questions that some of the reviewers of the paper asked and see if I can clear up any misunderstandings about ProFL. So the first question is, does the mutation engine change constants? So we based our mutation engine on a paper that went through and synthesized which types of mutations are sensible for Prolog. So a sensible mutation can be described as a mutation that changes the meaning of a program and does not cause it to crash. And a non-sensible mutation would either not change the meaning of a model or cause a crash or cause an infinite loop. So according to the paper, changing a constant to a variable or a variable to a constant does not change the meaning of the program. Does change the meaning of the program. Therefore, it is considered sensible. Therefore, we implemented it. So the second question is, what happens if the cause of the error is not an existing clause, but rather a missing one? So this is a really good question, and I think it's a bigger problem than just our tool. So I think in general, fault localization techniques are really good at work really well when the cause of the error is a statement that causes a fault in the logic of the program, therefore causing the test to fail. And it does not do well when the cause of the error is some missing logic within the program. So it's definitely something that fault localization techniques need to address. And lastly, discuss how the tool will fare when scaling up to larger programs. So that's hard to say because we had a really hard time finding bigger Prolog models, more complex ones that had accompanying test suites. But one of the things we could say for sure is that the runtime will be significantly higher. That's something we notice even with our test models, is that adding just a few tests exponentially increase the runtime. So that's something to watch out for. But as far as how to do, as far as accuracy, it's hard to say. And yeah, thanks everybody for listening in.